Let's assume that we have a path with 3 ASs, 1, 2, and 3, and that each AS has a public-private key pair. Let's assume that we have a network with 3 ASs and that each AS along the path has a public-private key pair. An AS can sign a message or a route with its own private key, and any other AS can check that signature with the AS's public key. So let's suppose that AS1 advertises a route for prefix P. So that route would contain the prefix as well as an address attestation, which we're not showing, but let's look at the path attestation. So as usual, the BGP announcement would contain the prefix P and the AS path, which so far is just 1, and the path attestation, which is actually the path to 1, signed by the private key of AS1. When AS2 re-advertises that route announcement, it of course advertises the new AS path to 1. It adds its own route attestation, 321, signed by its own private key, and it also includes the original path attestation signed by AS1. A recipient of a route along this path can thus verify every step of the AS path. AS3 can use the first part of the path attestation to verify that the path, in fact, goes from AS2 to AS1 and does not contain any other ASs in between. It can use the second part of the path attestation to ensure that the path between it, AS3, and the next hop is in fact AS2, and that no other ASs could have inserted themselves on the path between 2 and 3. This is precisely why the AS signs a path attestation with not only its own part of the AS path in the path attestation, but also the hop of the AS that is intended to receive the BGP route advertisement. To see the importance of this part of the path attestation, suppose that these ASs were not there in the path attestation. In this case, we have a very nice, well-formed BGP route advertisement for a prefix with the AS path suffix 21, and we have each segment signed. So an attacker could in fact take such an announcement and advertise substrings of this route advertisement as their own. Thus, an attacker, AS4, could claim that it was connected to prefix P via AS1 when in fact no such link existed, simply by stealing or replaying the path attestation 1 that's signed by K1. But note that in reality, AS1 never generates this signature. In fact, it generates the signature to 1. Or in this case, it would somehow have to generate the signature for 1, signed by AS1's private key. Whereas if AS1 only signed a message with its own AS in the message, such a segment or attestation could easily be replayed. There's actually no way that AS4 could forge the path attestation for 1 signed by AS1's private key, because it doesn't own this private key, and AS1 never generated a path attestation with this particular signed path. This is the reason that each AS not only signs a path attestation with its own AS on the AS path, but also the next AS along the path. This particular mode of signing not only prevents the type of hijacking that we explored, but it also prevents path shortening attacks. For example, when AS4 receives the legitimate route to ASP through the path 321, it would be impossible for the AS to shorten that advertisement to say 3.1, because it would somehow have to generate a path attestation for 3.1 signed by its own secret key. However, if it did that, the receiving AS would look for another path attestation with just 3.1 signed by AS3. Yet, such a path attestation would not actually exist. So, these path attestations can prevent against some kinds of hijacks, as we've seen. They can prevent against these path shortening attacks, and they can also prevent against modification of the AS path. However, there are certain attacks that path attestations cannot defend against. So, if an AS fails to advertise a route or a route withdrawal, there's no way for the path attestation or BGP-SEC to prevent from that kind of attack. Certain types of replay attacks such as a premature re-advertisement of a withdrawn route, also cannot be defended against. And of course, there is no way to actually guarantee that the data traffic travels along the advertised AS path, which is a significant weakness of BGP that is yet to be solved by any routing protocol.